Sunday morning, Rocky Mountain Ham is doing their Summer Fest out at the Adams County Fairgrounds. I believe it starts at 9 o'clock. If you're willing to go out there and get rid of some of your stuff that you don't need anymore and pick up other stuff that you don't need but you want, it's a good opportunity because they've taken over the weekend that Denver Radio Club initially had. So they're doing our club a favor by still hosting the Hamfest on the same date. And then the other thing is on the 30th, we're doing a DRC Saturday out at Prospect Arena where we have our field day. And it's Colorado's QSO day. So we're getting together at 9 o'clock out at Prospect Arena. And I know that Pete just signed on. And if Pete, do you have anything else you want to say about that? Otherwise, I'll turn it back over to Jerome.
Nope, just looking forward to seeing everybody at Prospect Arena for the QSO party, and I'll be out there setting up a little earlier than that, but we'll be out there just having some fun. So look forward to seeing everybody. And thank you, was it Tom, for doing an informal presentation? I really appreciate it. Thank you. I'm good.
Yeah, I guess with that, Tom, yeah, the floor is yours. Go right ahead.
Okay. By the way, I have to say, Pete, you have an absolutely beautiful green screen. I am jealous. Let me put it that way. You're supposed to have all sorts of junk like I've got behind me. Oh no, no AM radios, no 5 tubers. That just doesn't work.
Okay, we'll go back to that then.
Well, the scary thing is I can actually tell you what those 5 tubes probably were. So, that's what happens when you get to be old. Folks, the first thing is this is really definitely off the cuff. Therefore, please forgive me if I wander because I have a habit of doing that. That's just what you're going to have to, that is the toll you'll have to pay for listening to me. The other thing I'll tell you is if you have 20 hams and you put them in a room and you ask them what's the best antenna, you'll get 26 answers in a fist fight. It just happens that way. There is no such thing as a best antenna. Might as well get that one right now through your head. There are good antennas for your situation. There is no magic antenna. There never was. You can have somebody claim that they're in-fed half wave or they're vertical or they're step IR, which is a nice antenna, a little expensive. They don't make it. I won't sell it to you any longer. I mean, they're really nice, but they don't fit everybody's situation. So, with that in mind, let me start off with some of the things that we tend to make some bad judgments about. And the first thing I'm going to tell you is resonance. You'll hear people saying, first off, that a resonant antenna is better than a non-resonant antenna. And that is completely wrong. I'm sorry to tell you that, but that is wrong. Resonance is a design criteria, not a design goal. Now, what I mean by that is some designs require resonant elements. If you look at a Yagi, yeah, that radiating element is undoubtedly resonant. There are others. An in-fed half wave better be resonant, otherwise it's not going to work on any frequency other than one. You need that resonance so it works on all of the multiple frequencies going up from the one it's cut for. So if you have an 80 meter in-fed half wave, it's got to be resonant there so that you can do 40 and 20 and 15. One of the that is a requirement of that design. But if you look at a lot of antennas that are used by the military and by commercial applications, they won't be resonant. As hams, we got it made. A lot of our bands just go all the way up. They multiply part of that is historical. And the reason is they figured that we were going to put out so much cruddy noise that at least the cruddy noise and its harmonics would be still in the ham band. In other words, we'd be interfering with ourselves, not with somebody else. And that goes all the way back to when the Department of Commerce was controlling the radio frequencies. Remember, we started off after World War II with 200 meters because that was just worthless. That was way too high a frequency. They dumped on us a lot through the years. The other thing that happens is people don't know what we mean by resonant. You'll see YouTubers will do this. Here's a misconception. They'll have a center-fed dipole. They'll put their MFJ antenna analyzer on it or somebody else. They'll look at it and they'll say, the reactance is 0. It has so much resistance and 0 reactance. It's resonant. No, it is not. Or I should say, it may or may not be resonant. Being 0 reactance on the feed point impedance on a dipole, center fed, is not a measure of resonance. The IEEE defines resonance on a dipole as having current minimums at the ends. If you look at, you always see the RMS current on an antenna that looks kind of like a sine wave. It's not quite, but it looks kind of like a sine wave from end to end. And the current's always smallest at the ends when it is resonant. By the way, it's also a minimum if you double the frequency. It does 2 loops. And if you triple the frequency, it does 3 loops. But the current minimums are at the end. That's what defines resonance in an antenna. Now, I understand that the 0 thing makes a lot of sense because how do you tell the resonant frequency of a coil and a capacitor? You set the reactance equal because they are opposite. One's 90 plus, one's 90 minus. You set them equal and solve for the frequency, and you come up with that wonderful formula for resonance in a series or a parallel resonant tank circuit, for example. But that doesn't apply to antennas. And if you stop and think about it, that series resonant that's 0 ohms, it's only resonant at one frequency. An antenna is resonant at multiple frequencies. It's not a good comparison. It's, this is where it is in one place. It must apply everywhere, and it doesn't. It's a lot like you'll hear the term Q, which originally was the ratio of the reactance of a coil to its resistance. So if you had low resistance with a lot of reactance, you had a high Q coil. It's translated to a very sharply tuning coil in a good old crystal set. But you'll hear that term used for, that antenna is high Q or low Q. They're talking about bandwidth. Okay? Or they'll talk about a high Q filter. What? It's using the same kind of concept in multiple ways. And that's something you really need to watch out for when you start reading up on antennas. You can hear people even switch definitions in the middle when they're doing a presentation, which I hope I'm not doing to you. So resonance is not defined the way you think it is, and it isn't always necessary. Now, you may say to me, well, hold it, what do they use for non-resonant? They used rhombics. And a rhombic is a diamond. It's open on both ends, except, I'll tell you in just a second, they made a change. But it's diamond-shaped, and each leg is multiple wavelengths. And it definitely was not resonant. There are 2 things that they did which might surprise you. A rhombic natively is bidirectional. Its favored direction is through the diamond. But you don't want to go in both directions. You only want to go in one way. So what you do is you waste half the power by putting a load resistor at the far end, the direction you want the signal to go. The direction going the other way, it gets wasted in your load resistor. What they used is they used stainless steel rods to heat up to absorb the power because they wasted half their power, 3 dB. But they got to go one direction. The reason that they were using those rhombics is because they needed to transmit on a wide variety of frequencies and change pretty regularly because of jamming. Both the Koreans and the Chinese did, I don't think they do now, but they did a huge amount of jamming. And North Vietnam, too. That'll tell you how long ago. So you needed to keep sliding the frequency around so that your listeners could actually find you instead of hearing the miserable noise that the opponents were putting out. They couldn't have resonant antennas because you'd be out there changing all your antennas every day. Doesn't work out real well. The other group of people that needed that kind of versatility was Ma Bell. You know, it wasn't until the 60s that Telstar was finally launched. This is scary. I remember Telstar. That was the first commercial satellite. They were still using, at that point, it was coaxial cable, but it didn't carry a heck of a lot of signals from the United States to Europe. What they did a lot of is they used radio. It was all scrambled, so you couldn't understand it. It was a reasonable scrambler for the time. I don't think I put any national secrets out on it, but it was reasonable. But the ionosphere has this habit of changing. You may have noticed that at various times. You know, different frequencies work better at different times. They constantly had to switch frequencies in order to maintain contact as the day changed. You know, that's that D layer that sucks out 80 meters like nobody's business kind of goes away at night. So maybe 80 meters is the right thing, but you don't have the good F layer to bounce your 10 meters over. So they needed to have the versatility of using the same antenna system to use a wide variety of frequencies. And what they used was a whole bunch of Vs, horizontal Vs. They were just like 6 or 7 or 10 wavelengths on each leg, pointing to, well, really to Ireland. Well, no, take that back. They were pointing to England. And from there, it was being distributed. So they needed the versatility. They couldn't use resonant antennas. If you look on the web, you can go see there's a Titan missile museum down in Arizona someplace. And if you look, there is an antenna that was built by Collins Radio for them. It's a disc cone. A disc cone looks like a whole bunch of legs coming out with a layer on the top. They're really, really enjoyed by people that use scanners because you can get a disc cone that goes from like 25 megahertz to 1.3 or even higher gigahertz. So if you're doing a lot of radio scanning, if that's something that appeals to you, that's a wide antenna. It's not resonant anywhere. Well, Collins made one that works in HF. And if you look at that missile site, you will find this rather large, very expensive disc cone. If you travel down there, you can check in, explain that you're a ham, and they'll let you plug into it. Lousy gain. It's omnidirectional, among other things, but wide frequency. And you might think that a site that has nuclear missiles just might need to have the ability to use a number of different frequencies. That's also true of the feds, particularly the military. And if you go out to the federal, I think it's still there. It may be gone. Out off of Kipling, that whatever that thing is, where Remington Arm used to be, and with all the Fed Center. Here we are. See, when you're old, you go out there. There used to be a huge antenna farm, and one of them, really strange looking, kind of looked like a giant hex. What it was, an antenna called a log periodic. Log periodics look an awful lot like a Yagi. I mean, that's one format. They're a little strange because in between each element is a basic swap, but they are also very wide band. You can easily get a log periodic that would cover from, say, 100 megahertz to 1.3 gigahertz with gain, with good gain. I mean, I'm talking 12, 13 dB gain forward and about 15 to 18 rejection. They're flat as can be. If you go check the SWR, they're less than 1.5 across that entire range. All of those are necessary. Oh, and I started to tell you about one in particular that used to be out there that looked like, as I say, a giant hex beam. It really was a log periodic, other than it's that variation in size, except it was pointing up. It was an NVIS antenna. You know, the ones that we accuse each other of having when we can't get them up in the air. So that is one of the reasons why you would have a non-resident. I'm going to stop for a second and ask if anybody has any questions.
Hey, Tom.
Yes, sir.
Yeah, you were talking about the rhombics when I was up in Maine at Loring Air Force Base, a big SAC base. I ended up in the basement of the communications building, and there were 3 large coax cables sticking out of the wall. And I hooked an Atlas 210 to one of them, and man, signals were booming in from one direction. I hooked it to another, and signals booming in from the other direction. After a little sleuthing, I found out that out in the woods behind the building were 3 rhombic antennas, one aimed over the pole, one aimed west, and the other, one aimed west was aimed centered on Offutt. The other one was east over Europe. And I was sitting there with 100 watts. After hours, of course, I wouldn't do this while I was on duty, but after hours, I'd be sitting there with that 100-watt Atlas, and I could talk to Europe. And these guys, there's no way you're running 100 watts. And I went out and found this thing. Like you said, it was a rhombic, several wavelengths on a leg, and the terminating resistor was a whole bunch of stainless steel wire run back and forth in a pattern to make a non-inductive resistor. The other end of it, the feed point end, was a huge box. I can't remember the company that made it. It wasn't Collins, but it was a Ballon, 50 ohm to 600 ohm. And the nomenclature plate said rated 10,000 watts. So I don't think my 100 watts was warming it up very much. Also ended up with a antenna like they had out at the Federal Center. It's called an FRA 88. And had to work on a lot of those. And they also made a vertical, I can't remember the company, it might have been Harris that made it. It was a vertical rhombic or vertical
Log periodic?
Yeah, it was a vertical log periodic. There were 4 legs of it. There's only one half was vertical. The other half, they spread out the elements and went sideways on the ground. They used those for receive at the aeronautical stations. And those things went from 2.5 meg to 32 meg. And you put an SWR a rotector on it to test it out. And it was less than 1.5 to 1 off that entire range. So you could sit there and you could pick up one or more legs of that vertical LP antenna. They also had an inverted disc cone, which is another interesting one. That was also made by Collins, and a log periodic made by Collins called the 237B, I think, or 237C, which was it was a different construction, but the same idea. They had those Scott, Loring, and McClellan, and I think possibly at Offutt. But you had these things spread all over the place, and that was the exact reason. Was you depending on they didn't believe in the concept of a propped out circuit. They figured that there was some frequency that worked no matter what. And the other thing was, if signals are weak, just turn up the volume control on the amp. We were running 10,000 watt and 45,000 watt amplifiers. Interesting amps. 100 milliwatts in, 45 kW out. So now I've seen all these really strange antennas over the years, and some of them are still in use. I think others are probably in museums somewhere.
So there you go. See, I haven't been making it up. Did you notice that? I want everybody to nod. So I haven't been making things up. One of the frustrating things that you'll find if you try to do some research on antenna books, theory and so on, is that a lot of the engineering, the high-level engineering, was completed about 1960. Roughly after that time frame, they were all wrapped up into radar, so they were doing, up in the 2 gigahertz range, 1 gigahertz range. These days, if you look at the transactions of the IEEE on the antenna stuff, the antenna propagation group, they're talking about terahertz, not gigahertz, terahertz antennas. Now, theoretically, you could make, for example, a slot dipole for 80 meters, but that would be the strangest looking thing you ever saw in your life. Slot dipole is kind of the inverse of a dipole. You cut a hole in a big plate of metal. So that's not going to work, but it works at higher frequencies. Anyhow, they had pretty well gotten all the theory and all that stuff done by roughly the late 50s, early 60s. And at that point, what can I say? So if you go back to that range, this happens to be one that was originally published. This is Antennas by L.V. Blake in 1966. It was by Wiley. It was reprinted in 1984. And he talks about a whole bunch on log periodics because that was the new thing. That was kind of handy to have. And it's interesting. There is a reason, 2 things. One, I'm on to point out, this one I got used. Obviously, I wasn't buying antenna books at that point, and it is inscribed, and it says, July 21st, 1985, to Major Russell Smith with appreciation for assistance with errata in radar range performance analysis, Laurent Blake. So it was signed by the author to somebody who helped him on one of these other books. The reason I dug it up is for a long time, people have known that the impedance of a center-fed dipole in free space is 73 plus J 42 ohms. Now the plus J means it's reactance, and the plus means it's inductive reactance. 42 ohms. It ain't 0. So that's why I said, when you're saying, oh, well, if you get 0 ohms reactance on your MFJ, 235D or whatever the thing is, doesn't necessarily show that. Now, as you bring that antenna from free space down to the real world, the impedance changes. You know that because you know that the impedance of your dipole changes. It isn't 73 ohms when you're 20 feet above the ground for a 20-meter antenna. You can, however, you'll hear people saying, well, you can't have free space unless you're out on the space shuttle or something. No. Free space means that you are far enough away from, like a ground plane, the ground, or other objects, that your that they are located outside of what's called the far field. I'm going to talk about that in just a moment. But that's only, at worst, 4 wavelengths away, which means even at 2 meter, you can get your antenna up more than 8 meters, 24 feet. You can be in free space, guys, or close enough to it that you can't tell the difference. I admit that trying to get a 20 meter, or let's say an 80 meter antenna in free space, and let's take the little less strict determination. Say far field starts at 1 wavelength away, and that will be so 1 wavelength, 80 meters. Multiply that out, 240 feet. You got an antenna up 240 feet. I don't think anybody here has that. At least I would like to. I mean, mine's about 15 feet off the ground, to be honest with you. My infed. So yeah, there is difference, but you can't make that decision. Next thing, I am going to do something so it quits driving me nuts. If you can give me 1 moment, I'm going to turn off the stupid email so it quits making noise. Sorry about that, guys. Next thing, it's more the size of your antenna. It actually has a major part of how well it works. And we're going to talk about the near field and the far field. You'll hear that talked about. Then your antenna next to it is putting out a magnetic field. That's what the current does. The current makes a magnetic field. Magnetic field bands and it contracts because you're sending AC through it, right? Going bigger and it reverses polarity and all the good things of life. But when it contracts, sometimes it's contracting while it's building up on the other side. And that can actually cause it to pinch. So instead of getting a nice magnetic field around your element, you're getting this weird little bubble. You'll see that in some illustrations. You'll see that they draw it like an electric field rather than a magnetic field, but you'll see these like little bubbles. Well, what happens when you have a moving magnetic field? What happens? You generate an electric charge. And when you have a moving electric charge, what does it do? It generates an electric field. Guess what? You have just made yourself an electromagnetic wave. The effect of the magnetic field around your antenna decreases the further away you get. And by the way, next to your antenna, that's what they call the near field. But it decreases as you move away from your antenna. And it decreases on the cube. Okay? In other words, it's like the cube of 3 is 27. 3 times 3 times 3. The cube tends to get really big real quick. But the wave decreases on the square. So as you move away from your radiating element, at one point, and this they can't figure out, there is no absolute definition, trust me. At some point, the effects of the local magnetic field are so limited that they no longer, in effect, feed back. Your ground feeds back. I'm not talking about the propagation pattern. I'm talking about what affects the impedance of your antenna, for example, as you bring it closer to the ground. At some point, it's far enough away that it has no effect any longer. That's where the far field starts. The far field is where you start getting weird lobes because you're interacting with the ground, which is reflecting things, and they constructively or destructively add. In some places, they're in phase, it gets bigger. Other places, doesn't get out of phase, it gets smaller. And so that's why you get these weird Well, they're not weird, but you get them anyhow. These lobes on your antenna, did you see on the vertical, for example? If you stick the one wavelength is probably not enough. The German radio company, it's a national thing, claims it's 4 wavelengths. What does this mean to you? What does this really mean is your antenna, let's say you're doing 133 feet. I only think, sorry. If it's 2 wavelengths with 266 feet, tell me, do you have any houses that are closer to 266 feet your antenna, including your own? All of these things will impact how well your antenna radiates and how well it receives. That is reciprocal. So here's my next warning to you. The mathematical models, the ones like Easy Neck and whatever the one that's out of Europe, 4NEC, I think is the name of it. They are absolutely wonderful tools to model, but they have the same reality or the same relationship to reality as making a guess. They don't, for example, know about your neighbor's house. They don't know what your ground is really like. Yes, they put in some corrections, particularly with the Easy Neck has there's some corrections built in there. And then the NEC 4, that's the numerical electromagnetic computation is what that stands for. It was written out of, God help us all, it was written in Fortran originally, Lawrence Livermore Lab. The NEC 4, they charge you have to have a license. NEC 2 is free. It is absolutely a great program to say, well, this is kind of what I expect, but it is not reality. It's a model. It's a beautiful model, but it's a model. So please don't use those programs to prove something about how you have deployed your antenna. Put it bluntly, the only way you can tell you got a good antenna is to transmit on it and see if somebody receives. I'm sorry, that's all there is to it. Yeah, you could get out there and do some field strength measurements and that sort of thing. And it's a good pointer, but it is not reality. Okay? That's going to be my controversial one. Anybody want to slap me down on that one? Come on, MB0BN, you want to slap me down. I can see you grin.
What's the definition of a model? It's a small, not working example of an object.
You've been around the military too dang long. Models actually can be very valuable. But please remember, they are models. And I'm not even going to touch climate warming. I'm not going to touch that third rail, I guarantee. So that is my next point. And Ron, I'm getting a little long. Do you want me to keep on going?
You're just fine. Not a problem.
Next thing. This will get me in all sorts of trouble. And that is the idea that a end-fed half wave has to have a counterpoise. You will see that there's articles in QST that talk about it. There's some stuff from Australia that says, oh, this is what we've discovered. You need 1/10 of a wavelength counterpoise. First off, the term counterpoise is from the original patent for the Marconi antenna before World War I. It's a quarter wave vertical. And when they patented it, they put the wires going out. They said, well, those are counterpoises. Well, think what a counterpoise really is. They knew what it was. When you're building a bridge out, you need to have some weight on this side to keep it up. Otherwise, it'll fall down. So, counterpoise is a counterbalance. And the idea that you need that is a little bit peculiar. What probably is the reason that counterpoises assist in many cases is when you add it on there, you're basically changing the feed point. You got this long in-fed half wave, got a transformer, and then you got this quote counterpoise. Or maybe it's the coax itself. What you're doing is you're taking the feed point from the end and moving it in a little closer to an off-center fed. End-fed half waves in particular are very, very, very sensitive to their environment. The endpoint impedance is really touchy. Probably the best way you could do it, although I don't have it that way, to get the closest is to actually do it as a V with the endpoints fairly close, well, say 3 feet above the ground where your transformer is, and then go up as a V and support the center. Those tend to match better than anything you got. But that's not what I have the ability to do. So guess what? There is no perfect antenna. End-feds work very well. Another example of an end-fed half wave is the J-pole. A J-pole is a quarter wave piece of open wire transmission line. That's what the J is. With a half wavelength end-fed stuck on the top of it. If you stop and look at a quarter wave stub and you short one, if you have just a piece of quarter wave, even coax, and you go measure the impedance at the frequency that it's a quarter wave for, if you have it open on one side, it'll look shorted. And if you short the other side, it'll look open. It flips whatever's there. That's why you can make a trap when you're at field day and you need to get rid of that guy doing 20 meters next to you, or worse, 40 meters next to you, and you're on 15. You can make a trap out of quarter wave coax. Flip it in your line. Works pretty well, as a matter of fact. If you look at the J, it's shorted on the bottom. So that's 0. The top must be very, very high. What's the impedance of an end-fed half wave? Very, very high. So now you have a match. And then you attach your coax, moving it up and down, to find the point between short and open. That's 50 ohms. That's what it is. And if you attach it correctly, they work beautifully. And guess what you don't need? You don't need a counterpoise. Sorry. That brings up the next thing, which drives me totally nuts, and this is just a personal thing, and that is the word un. You'll see it. There's an LDG 9-to-1 un. What the heck is an un? Balun makes sense. It's going from a balanced antenna to an unbalanced coax. Balun. You're connecting a unbalanced to an unbalanced? I think that's a barrel connector, isn't it? It's where, because so many people use transformers for their balance, that's one form. There's a lot of forms of balance. You can wind up your coax. You can put some ferrite beads on there. Those are also balance. But because so many people use transformers, basically wideband impedance transformers, although it may be a 1-to-1, because they use that, and that was a balun. Well, if you've got a transformer that's on the unbalanced, it must be an un. That's a silly name. That is a wide band impedance transformer. Personal. You can ignore that one entirely. That just drives me nuts. The when you have a balun, which I said could be a transformer, or you wind up. What are you doing when you're winding up coax or putting ferrite beads on it? You're increasing the impedance of the outside shield. You're not affecting the inside of the shield at all. And you're not affecting the inside conductor on that piece of coax. But you are increasing the impedance on the shield. And so that when you're sending power up and it hits the antenna and you've got that other path, which is the outside of your shield, available, oh, hey, doesn't know. It's going to go to the antenna. Well, center conductor, one side of the dipole. The other side, the shield, the other side of the dipole, but it's going on the inside. The field is contained inside, it's not DC. And then it can curl around and come back. And that's where you can cause all sorts of strange pattern problems because it's part of your antenna. It's radiating on the outside. So you put something to increase the impedance of the outside, not on the inside. The outside does not contribute to your SWR because it's not reflecting back the same way. The inside, you've got power coming back on the inside of the shield. That's why you have a standing wave, because they will add and subtract, and so you end up with this standing wave depending upon the length of your coax. But if it were going on the outside shield, when you start putting ferrite beads, your SWR would go down. I haven't heard anybody saying that's a good idea. Sorry, your SWR is not affected by that. It's not going on the outside. You will find some people suggesting, and in many cases, not in many, in some cases it makes great sense to put what effect, they call it a choke, a current choke, near your radio. And the reason is because your coax on the outside, remember I keep talking about the outside, can pick up noise from the air conditioner and from other sources. And if you put a choke on it, again, you're increasing the impedance on the outside. It isn't going to come back to your radio. So you can actually reduce some noise. That doesn't always work, and a lot of times it's not necessary. Okay, I've covered that one. Bob, you want to yell at me because you're still looking at the screen. Anybody have anything on there? I'd say Tom, but we probably have more than one.
I've got something to talk about on antennas.
Go for it.
I recently purchased a small book. I have the ARRL antenna books, the RSGB antenna books, and a few other. This is about 3 pounds of book. Yeah, you got it too, huh? Anybody wants to read about antennas, this is the book to get.
It's Rob Hamel's antenna book. It's put out by the German version of the ARRL. And I'm sorry, it beats the ARRL antenna book all to heck with its detail. And the only thing that you're going to find on it is it was translated into English by Hans Schwartz. And there are some times when Hans gets a little Eastern Nebraska in his translation. Once the Rady Jake.
Tom, I also have the German version of it, one of the earlier versions that I bought when I was in Germany. And I tried to wade through it with my German to English technical dictionary, and I think I got about 8 pages in before I gave up. So when this showed up, I've been trying to buy it. I tried to buy it through RSGB, but they wanted 100 pounds to ship it. And DX Engineering has, as you probably know, they're the only ones in stateside that have it. But I highly recommend it. If you want to know anything about antennas, one of the things that I found in there was there's a lot of information on commercially made antennas worldwide. The stuff that's made in Italy, Germany, England, United States, all over. And they give things like all the dimensions and everything on them, which really, and the original book was authored by somebody who was born in, I think it was 1916 or 1918. He was a communications guy for the opposing forces during World War II. And he's gone now, but all the stuff in it, the translations and everything, just have to remember that it is a translation, and sometimes you have to, it's sort of like reading something that was translated from Japanese or Chinese by somebody who was not fluent in either Chinese or English.
Yep.
So I think you'll probably agree with that one, but it's, the intent is there, the information is there, and it beats the ARRL antenna book all to hell.
You got it. Among other things, for example, if you look up a Yagi or one of log, log periodic, it gives who designed it and what the patent numbers are, even if it's in the United States. So I cannot recommend that any more highly. It is absolutely worth it, and it's not. You don't have to be a genius to use it. It's just a tremendous resource, and seriously, it does beat the heck out of the ARRL. Now, if you want to see another book to drive you totally insane. Oh, by the way, you got yours from DX Engineering. I think I got mine from Gigaparts, to be honest with you. Maybe it's from DX, but
DX Engineering is the only stateside distributor of it that I know right now.
And it's about $60, as I recall.
$87.50 plus shipping.
It's heavy.
That's free shipping though if you go over $100. So I bought something that was like $15 more and got free shipping. So
now, if you really want to go nuts, here's another one you can get. This one is from Cambridge Publishing, which is Harvard University. That's their publishing house, because they publish for MIT. And seriously, if you ever want to go completely nuts, this is a great one. It was originally published in 1959. They still print it. It's called The Theory of Linear Antennas by Ronald King, who was a professor. He's long dead. Professor at MIT. He took a year and 2 graduate students to write it. He did it on sabbatical. If you've ever wanted to have any kind of mathematic anything for any kind of linear antenna, there you go.
this is it. Yeah.
It's absolutely fantastic. But you have to be crazy.
The other one that I saw was really good was Laporte. Wrote one on antennas, and I think it was published 1952. And it's got some really good stuff in it, but they got a little bit wild with the math. Actually, a lot of bit wild with the math.
Okay, I think I'm through with antennas at this point, unless somebody has a particular question.
Maybe somebody has an answer.
I got a question.
Yes, sir.
I think I know the answer to it, but you were talking about antennas and kind of with the modeling of those antennas, you kind of get the pattern of radiated power in essence, right? And we're
Right.
kind of talking about that. And you're talking about near field and far field and kind of how far field you kind of lose one part of what's going on to know that you've got that. So when you're looking at those models and they're modeling it and that power, that radiated power, are they modeling that out basically to the far field to get what's going on there? Because you're talking about how it'll bounce and it'll react and do that type of stuff. Is that where they model it out to, or
They
approximately?
actually model it beyond. They
Okay.
assume of your ground, so that's how they can get the actual. The real pattern is more generated in the far field. I mean, it goes the whole thing, but that's
Mhm.
where the most impact is. They're
Okay.
doing all of it there.
Okay.
And don't take my well, don't do that. Don't use models. Don't take that seriously. They're actually very good. But I saw somebody using a model to say, well, if you swap the coax on a J pole, it gives you a different pattern. Well, I'm sorry. That's uh, the work that they did on those models, the NEC2 stuff. Yeah, it is brilliant work. It can only be done well. You can do it by hand, but you'd have to be crazy because they're using something called the method of moments, and they're taking that antenna and breaking it up into little tiny segments, and then they calculate for each one of those segments individually, and then they calculate the impact of the segment next to it, so they can then start joining all those things. It really came from mechanical engineering is really where the idea came from, and they applied that, and it truly is brilliant work. I don't want to knock them at all, but I I just don't like it when you use a model to prove something.
It gives you an idea of what might happen, but if you start talking about things like switch the coax, the shield and the center conductor on the coax on the antenna, and say you're going to come up with a different field, different pattern, what you're actually saying is that the coax is part of the antenna, like as you alluded to with the fact that it radiates from the outside of the coax coming back. If you're feeding a balanced antenna with an unbalanced cable without some sort of interface to convince it to do something different. And it actually is, like you said, mechanical engineering. They used it a lot for stress analysis on mechanical devices.
Steam
And
locomotives.
second,
Steam locomotives.
yeah, way back then. But my brother-in-law was a mechanical engineer, did aircraft engines, and that's the method of moments is what they did to determine just how far you could force a recip engine before pieces started disassembling. Was it rapid unscheduled disassembly?
So, with that, I think I am probably through. I hope that you were able to put up with my little presentation, and I hope you got some information out of it. I really do. I am going to make a plug for something. If you happen to have an all mode UHF VHF radio, we would love to have you get on at 8 o'clock in the morning on 144 200 upper sideband. We run the Beam Spinners net, and there's people from Colorado Springs and Black Forest all up to Cheyenne. Your best bet is, frankly, to have a horizontally rather than the vertically polarized antenna, unfortunately. But we'd still love to have you. And then tonight, in fact, I'm going to get on it in 5 minutes. Monday through Friday, there's the net run at 8 o'clock and you can find it on the Beam Spinners Net website. There's a listing of the frequencies. On Monday, we do 2-meter upper sideband. On Tuesday, it's 220, which I can't do. Wednesday, which I'm going to get on in a moment, is 432.1, 70 centimeter. Tomorrow will be 1296.1. 23 centimeter. And Friday is 9:02. If you have anything does that. So Monday through Friday, there's a net at 8 o'clock. It's very, very, very loose. Trust me. And we would love to have you join us, guys. But we have fun. And frankly, my little 10 watts can make it up to Cheyenne pretty regularly, unless the conditions are really bad. And I think on there someplace is K0GPA, Mr. Bob, and he gets on in the morning. So it'd be fun to have you join us. So that's my plug. And with that, Daron, I will turn it back to you and say thank you for allowing me the chance to talk.
Thank you, Tom.
Thank you, Tom. Absolutely. We can't thank you enough for that, and hopefully that motivates other people. This was just off the cuff. So if anybody's interested in giving us presentations in the future, that's motivation enough for me at least. So thank you enough for that. So if anybody else has anything, otherwise we'll probably end it there. All right, well, again, youtube.com/Denver Radio Club. This was recorded, so if you want to go back and watch that recording, that's on there. And if you missed it,
oh, Lord, no. Now somebody will catch me.
that's all right. No worries. Perfect. Well, thank you all again. Have a good evening.
Thank you all.
Hey,
Thank you,
Tom, if you're around a little bit later, I'd like to talk to you on a landline.
Yeah.
I got a net tonight.
Yeah, I've got a net. I've got a net in just a few minutes to join.
The 432.1.
Yes, sir.
I'll see if I can throw something together to get on there.